Okay, so, all right. So we are talking about classification. On Monday, we covered the Bayes classifier and the naive Bayes classifier. And today we'll talk about two other classification methods, the k-nearest neighbors classifier and support vector machines. So this is kind of your week on classification, and you've got some homework where you'll have to code these things up, okay? And again, the point of the homework is for you to get to think about these things and to give you some exercise in, implementing an idea in code, which I think is an important skill to develop. K-nearest neighbors is an algorithm that is popular and is readily available, and so in R you can just use KNN, and there's all sorts of other packages. There's all sorts of other things, but I do think there's merit in having to kind of create your own, write a little bit of code. And it only takes maybe a few lines to achieve the task, but I think it's important to develop your ability to take an idea and put it into something that runs. And anyway, I just want to kind of walk through and explain the k-nearest neighbors algorithm. A student later told me that that she had an interview with a company, and they asked her to do whiteboard explain the k-nearest neighbors algorithm, and so she had to kind of write down the algorithm and the pseudocode and stuff like that. And so so who knows what kind of interviews you will have. This could be something that you face, or maybe that was just that one student and her interview. But anyway, this is how the k-nearest neighbors algorithm works for classification. Okay, and so we start off with training data. Okay, and all of the training data is labeled with a class. Okay, and so you have your data points. They're all labeled with this belongs to class A or class B or class C, or in the case of your homework, it'll be like, this is Virginica and this is Setosa and this is versicolor or something. And then what happens is when you get a new test case, okay, when you have a new case, what you have to do is you have to measure the distance from that case to every single other point in the training data, okay? We often use Euclidean distance to measure the distance to every single other case. And it is for this reason that I would say k-nearest neighbors has fallen out of favor, in that this step is very computationally expensive. Okay, so you have to measure the distance to every single data point you have in the training data. If you have 1 million data points in your training data, this is a computationally expensive step. Okay, and then once you measure that distance, you're going to sort the resulting distances, and then from there, the k-nearest neighbors, that name comes from the fact that you will sort and choose the observations with the k smallest distances here. Okay, and then once you select the k observations with the smallest distances, that is your k-nearest neighbors, you will select the class in the training data with the highest representation. Okay, and that's going to be how you classify your new observation. Hang on a second. All right, and so so that's how we're going to do it. A frequent question is, how do we choose k? And we don't really have a great answer other than use cross-validation and see how different values of k perform for on your training data, to kind of get a guess for how for what size k use. Okay, so you know, when I'm going to show you an example in 2 dimensions. Okay, we're gonna I'm going to show you a picture in 2 dimensions, and when you look at the 2-dimensional picture, it's going to be very easy to kind of tell which data points have the shortest distance in as far as Euclidean distance goes. And so you might wonder, like, why is it necessary to measure the distance to every single other data point? Okay, and the answer is that in 2 dimensions it's easy. Okay, our eyes and our brain are set up to be able to kind of estimate distances easily in 2 dimensions. But in a higher dimensional setting, like if data exists in 17 dimensions, knowing whether 2 points are close to each other or far apart from each other in 17 dimensions is not going to be an easy thing to do. So so that's why you end up having to just measure the distance to every single other data point anyway. Okay. Sometimes you end up with a tie. So if there's only if you only have 2 classes, like you have class A and class B, and then you choose K to be odd, then you should never get a tie. Okay. I mean, there's a very, very rare possibility that you actually get a distance tie, but in general, if you have K as odd, you're not going to have you're not going to get a tie, right? So if you have if K is 9, you know, the closest you'll get is like a 5-4 split. Okay, but if you have K to be an even number, or if you have more than 2 classes, like if you have 2 classes, even with K equal to an odd number, you can get a tie, right? You can get something where it's like 4, 4, 1. Okay, you have 4 of class A, 4 of class B, and 1 of class C. Okay, then you have a tie between class A and class B, and how should you resolve the tie? Okay, there is we don't have a hard rule as far as how ties should be resolved, and so we have a few options, and kind of depending on the scenario, you might think about how you should deal with the ties. Okay. We have a question. It says, how do you deal with categorical variables when calculating distance? Okay, and that's a good question. And K nearest neighbors is basically a numeric algorithm for numeric variables only. Okay, and so if you have a categorical variable, you have to convert it to be numeric somehow. So either you choose 0s and 1s, or you choose some other value. Okay, maybe you have an ordinal variable and you can change it from, you know, small, medium, large, extra large to 1, 2, 3, 4, and maybe that makes sense to use for different numbers. But yeah, if you have a categorical variable, like somebody has a red car, blue car, white car, black car, things like that, there isn't really a way to, a clear, straightforward way to make it numeric. You can say, well, you can make a column for red and it'll be 0 or 1, and then a column for silver and 0 or 1, column for black cars for 0 or 1, white car for 0 or 1, or something like that. I don't know. Dealing with categorical variable is difficult. One could argue that having a categorical variable has already kind of done a tiny bit of classification already, and that it already kind of divides the group data into subgroups. But yeah, K nearest neighbors is originally designed for numeric variables. But yeah, turning a categorical variable into numeric is kind of a challenge and something you have to think about. There's kind of a subdivision of machine learning called feature engineering, and it's all about basically getting numeric values, numeric features out of different variables, either looking at categorical variables, looking at, you know, some kind of combination of these things to develop a numeric variable, which is called a feature. And that's kind of feature engineering. We're not going to really get into that. We're just going to talk about straightforward k-nearest neighbors on a numeric data set. Okay, but let me go back to ties. And so, you know, one solution is just if you end up with a tie, you just say this is unclassified. Okay, you don't pick an answer. Okay, another option is to pick switch to one nearest neighbor for resolving a tie. And when you switch to one nearest neighbor, you will almost never get a tie as far as the nearest neighbor. Okay. You could just also select randomly among the groups that have been tied. So if you have 3 groups, A, B, and C, and A has 4, B has 4, and C has 1, you can just randomly select between A and B. Or you can say among the top tied groups, select the group with the closest neighbor. So you can say, well, between A and B, which one it has the closest neighbor? And that's not necessarily the same as using the one nearest neighbor, right? So in the split, if you have k equal to 9 and you get 4a, 4b, and 1c, it is technically possible that the one nearest neighbor is the c, okay? That class C is the one nearest neighbor, but there's only one of those observations. And so if you use one nearest neighbor, it would be the closest observation. Maybe that's class C, but then you can say, well, as far as the ones that were tied, A and B are the closest, and then you pick the one with the nearest neighbor there, okay? So these are different ideas that can be used for resolving ties. But yeah, a lot of times any of these would be fine, okay? All right, so as far as an example goes is I'm gonna just set up some training data here. Okay, I'm gonna have 14 observations that are coming from class A and 10 observations coming from class B, okay? And I'm gonna kind of graph these, and we're gonna just plot some of them to be red and some to be blue, okay? And here's our plot, okay? So this is kind of, these are my red data points and my blue data points, and we're gonna get a, we're gonna put in different test cases, and we're gonna use the k-nearest neighbors algorithm to kind of help us classify whether a test case should be red or blue, okay? And so, you know, I mean, if we had to kind of draw a boundary, we'd probably draw something around here, and anything, you know, anything over here would probably get classified as red, and then anything over here would probably get classified as blue. And then, you know, there's a question, I'm intentionally gonna pick some points kind of in the kind of overlap region, boundary region, and we'll try to see whether a point gets classified as red or blue. Okay, so I'm gonna put a dot right here, and we're gonna ask, should this test case be classified as red or blue? Okay, and so for the k-nearest neighbors algorithm, what we're gonna do is we are going to first start off by measuring the distance from our test case. Okay, so this is our test case right here, and we're going to measure the distance to every single other data point here. Okay, and so so we measure this distance. Now, I intentionally did not include the code for the algorithm in these slides because I want you guys to do that for a homework exercise, okay? I've at least written out the steps, and I think, you know, figuring out these steps are, you know, taking those ideas and putting them into code is a reasonable exercise, okay? So we measure the distance to every single other data point, and then we're going to pick the values that, the data points that are closest. Okay, so we've got, so here k equals 1, our nearest neighbor to this data point is red, okay? And I've illustrated that by drawing a circle with the radius of going to the nearest data point, and we see there's no other data point that is closer. Okay, so for k equal to 1, this test case would get classified as red. Okay, here, if I choose k equals to 3, okay, we're going to have 2 red and 1 blue. Okay, and so with k equal to 3, the 3 closest data points are this blue, red, and red values. Okay, and so with this test case is going to get classified as red because we're going to say, you know, what are the votes? I guess I don't know, votes of each of these things. And so we have 2 red votes, 1 blue vote. So this test case right here would get classified as red. As I increase my k with k equal to 5, okay, then inside this radius I have 3 blue points and 2 red points. And so this test case is going to get classified as blue. Okay, so when we choose different values of k, the test case is going to could get classified as different values here. Okay, so we get 3 blue and 2 red, so this is going to get classified as blue. Okay, all right, with k equal to 7, these are the 7 nearest points that I have here. So I've drawn so the 7th nearest point is this red one. This blue dot comes very close, but is just a little bit farther away than this red dot. Okay, so it is not one of the 7 nearest neighbors. These are the 7 nearest neighbors. And so among the 7 nearest neighbors, 4 of them are blue, 3 are red, and so this test case is going to get classified as blue. Okay. Anyway, even if this was the 7th closest point and this was a little bit farther away, then then you would have 5 blue and 2 red, and it would still get classified as blue. But this illustrates k equal to 7, and that's what we have here. So for the different values of k, you might get different answers. Okay. All right. Here is another test case. And this one is a little bit more into the red territory, and we can see how this is going to behave with different choices for k. So again, when you run the k nearest neighbors algorithm, you start off with your test point, and you're going to measure the distance to every single other data point in the data set. Okay, and so now we have the distances to every single other data point, and we're going to find which observations are the nearest ones. Okay, hang on a second. Okay, everything's all right. Sorry. Okay, so for here I've got for k equal to 1, this is our nearest data point to our test case, and it's red. So we're going to pick red. With k equal to 3, these are the 3 closest data points, and 2 of them are red, so this still gets classified as red. With if we choose k equal to 5, the 5 nearest data points are these 5. 3 are red and 2 are blue, so we're still going to pick red. And with k equal to 7, these are the 7 nearest data points. 4 of them are red, 3 are blue, and so it still chooses red. Okay, so this test case, it's not super far into the red territory, but it is into the red territory, and so that's going to get classified as a red data point. Okay, so that's basically it. That's the k nearest neighbors algorithm. you know, we measure the distance to all of these other data points, and then we just have to find the ones that are closest, okay? Now, you don't have to draw these pictures like this. All you really have to do is you just need to find the table of all of these distances, and then you just sort them, and then you say, all right, I'm gonna just pick the top 5, or I'm gonna pick the top 3 or whatever, however many data points you have, okay? This is, so here's the question. It says, if there are 3 blue points all closer to the test case than the 4 red points, will we still choose blue? So, okay, so the question is, all right, with k equal to 7, you know, let's say the 3 closest points are blue, and the remaining 4 points are red. You know, should the closer points get, you know, more of a vote? Okay, so right now, with the regular old k nearest neighbors algorithm, everybody's vote counts the same, and so because there are 4 red points and 3 blue points, it's going to get classified as red. Okay, even if the 3 closest points, right, the 3 closest points are blue, it's going to be 4 red outweighs the 3 blue, and therefore it gets classified as red. Okay. There is another algorithm, because somebody basically had a similar thought and said, well, you know what, the ones that are closer, their votes should count more. They're the ones that are most similar to the test case. And so there's something known as the weighted k-means, k-nearest neighbors algorithm. So not k-means, sorry, k-nearest neighbors. There's the weighted k-nearest neighbors. And you have a formula for determining how much each of these, like the weight of each vote, okay? And so the closer points, those votes count for more, right? And then the points that are farther away, you know, those votes count less, okay? And so, you know, it might be like inverse distance. It will be like the weight of the thing, or inverse square distance. That'd be kind of like a gravity type of thing. And so in that case, if you the split where it's 3-4, if the 3 closest ones are blue, those, even though there's only 3 and there's 4 red ones, and k equal to 7, you know, the 3 that are closest, maybe they weigh more, and so those 3 votes might outweigh the 4 votes that are red in the other direction, and it could be classified as blue. So so you know, that's another possibility, and that would be the weighted k nearest neighbors algorithm, and that's not what I'm covering here. I'm not using that. Another one, why don't we just add the distances? Yeah, I mean, again, there's different different options. Yeah, so in terms of like weighting, how to weight them, and you can say, well, I mean, if you add up the distances, are you saying that the lower distance is better? Because in that case, then if you only have one observation that's closest, and you have a small distance, and you have like a whole bunch of observations that are farther, that are red or something, one blue that's really close by, and a bunch of red observations that are farther, then adding up the distances, you'll get a larger distance for more votes, which I think would not be what you want there. Okay. Okay, another question. It says, so these test cases are part of the N observations in the training data, correct? In other words, it's almost like leave one out cross-validation where we use N-1. Okay, yeah, so actually, you're using the full training data set, okay? So I'm not doing cross-validation yet, okay? And actually, I don't have any slides here for cross-validation, but yeah, these are all the data points are part of your training data. You have N observations, and you're gonna, whatever your test case is, okay? So this test case is not part of our training data. This test case is unlabeled, okay? So it's not that there's N-1 observations. We're using all of the N observations. We're looking at all N observations, and this test case is unlabeled. And the question is, how should we label this test case? Okay, so we're using all N observations. We're not taking out any one observation. We're just taking this test case, which we don't know the answer to, and we're going to measure the distance to every single other data point in our training data, okay? So, so we look at this, and then again, we say, you know, we're going to classify it red because the nearest point is red, or we're going to say k equals 3, and out of the 3 closest points, 2 of them are red, so therefore this should be red, okay? Out of the 5 nearest points, 3 of them are red, therefore the test case should be red, or out of the 7 nearest points, 4 of them are red, and therefore the test case should be red, okay? And technically, what I'm going to show you is, so this is just one test case right here, okay? And what I can actually do is, because I've got the computer, I can actually try out like 1,000,000 hypothetical test cases all across this kind of the graph here, right? I can say, well, what if I put a test case right next to it, right over here? Or what if I put a test case right here? What if I put a test case right here? And I can do a whole grid of test cases, and we can see how those test cases will get classified, right? So this test case gets classified as red, and that's what this next plot shows, okay? So this plot, and let me go back. So this plot and this plot have the same. So if I switch between slide 13 and slide 20, the training data is exactly the same, okay? That's kind of what I'm trying to show here. Okay, so if you look at where the blue and the red dots are, the blue and the red dots are in the exact same position. But what I've done is I've created a grid of test cases, okay? So I've gone through, and with the computer, I've gone through and I've, I hope you guys can see this. All of these little dots, these are just tiny little test cases, okay? And, you know, I asked the computer, please classify every single one of these test cases using k nearest neighbors, and use k equal to 1, okay? So using the 1 nearest neighbor, we're gonna go through and tell me what is the, how would this dot right here, can I do this? Like, how would this little dot get classified? And at this point, this dot gets classified as red, okay? But if you move over just a tiny bit, this dot, this nearest neighbor is blue, okay? And so, so I created a whole grid, and that's what this code is. We just created a giant grid of these things using, I did expand grid, where I went from -3 to 3 and -2.5 to 2, and I did 101 of these things. Expand the grid, and then we asked R to do to run k nearest neighbors with k equal to 1. Okay, so I just used the k&n function. Okay, and so we go through and we test every single one of these points, and we say, how would this get classified? And with k equal to 1, this is the boundary region that gets created. Okay, and so this is just kind of, it's drawing a line between where the grid ends up getting classified as a red point versus a blue point. Okay, now if I had a higher, if I bothered, I could make the grid even finer, and these would end up being straight lines and not little jagged lines. But we're basically getting a grid, and you can see, you know, the boundary is formed where basically it's equidistant between the kind of the two nearest points that are red and blue, right? So anything on this side gets classified as red, anything on this side gets blue, so on and so forth. Okay, so we have a question that says, are small k values more prone to overfitting, and or is it unrelated? The answer is yes, small k values are prone to overfitting. Okay, and so so we will see that happen. Okay, so so I'm just kind of using the same example data where it's fairly sparse, but we will see if I increase the number of data points, a smaller k is definitely bound to more likely to overfit. Okay, and so, you know, this red point feels a little bit of like an outlier, and so we're getting kind of like this like peninsula of red, right? So if blue is water and this is the land, this would be like, I don't know, it's not quite Florida, but it's the peninsula that sticks out into the water, and maybe you know, it would feel more appropriate to kind of classify these dots as blue over here, okay? And so if I increase k equal to 3, all right, we'll see that, you know, kind of the points that are over here end up getting classified as blue, okay? And so, you know, interestingly enough, with k equal to 3, our boundary ends up like this. We get a few more red points over here because if you go right here and you say, what are your 3 nearest neighbors? It's going to be kind of these 3 where you have 2 red and 1 blue. And so, you know, that's just kind of an interesting thing. So with k equal to 3, our boundary ends up being, you know, less, I don't know if jagged is the right word, but it's the kind of the shape of the boundary will just changes, okay? With k equal to 5, the boundary also, again, the shape becomes, there's less sharp angles in the I don't want to say less sharp angles, because there's definitely some strange turns here, and it's all based on what data points are closest, okay? But the overall shape is that, you know, this is more likely to form kind of things that protrude into the different sectors, and as k increases, you get something that looks a little bit more like, and again, smoother isn't the right answer, but one that is less prone to form these very kind of extreme shapes, okay? So with k equal to 1, 3, 5, 7, okay? And again, this was achieved by doing a whole grid of points and then just asking, how would you classify this dot, you know, if I used k equal to 7, okay? And these dots would get classified as red, but right over here, these dots would get classified as blue, okay? And this is, we can achieve this using using the computer, because it can do all of these things. Less curvy, yeah, perhaps that would be a descriptor for how the boundary changes, okay? Here, I'm going to kind of just show you the boundary regions that form where smaller total arc length, yeah, that's another way to describe it. So here's a case where, you know, your data is, it would be a lot harder to kind of draw a clear-cut boundary in something like this, where there's like, you've got blue points that kind of end up in the red region, you've got some red points that end up in the blue region. How should this get classified? How do we draw a boundary between red and blue using the k nearest neighbors algorithm, okay? So if you use k equals 1, all right, well, I don't know, just picture in your head how the boundaries should form, right? With k equals 1. Can you even imagine what this would be, right? So if I do k equals 1, what would this area get classified as? So this, there's going to be kind of a boundary between these two data points. Stuff right here will get classified as red, and just a little bit between, like halfway between the midpoint between these two, it'll get classified as blue, okay? And, you know, there's also we're gonna get some kind of boundary between these two red and blue points and things like that. And so anyway, let's just see how you did, all right? And then, okay, and then here's a blue point right here, okay? We're gonna get like an island all by itself, okay? Or I guess if red is the land and blue is the water, we're gonna get a lake, okay? A blue lake here, okay? Where there's gonna be kind of a zone that gets classified as blue, because you know, dots that are close to here with k equal to 1, dots that are close to blue will get classified as blue, and then dots that are just a little bit closer to the red are going to get classified as red, okay? And so this is what ends up happening. This is the results. We get, this is kind of the blue lake that forms. You also get a blue lake a lake that forms here and a lake that forms here, and you get like a little island of red, and you get this kind of this peninsula, or these, I don't know, whatever you want to call these things that that form. And here in the region with k equal to 1, so one thing about k equal to 1 is that there's going to be no misclassifications in your training data, right? So in the training data, no dots will get misclassified because you're using k equal to 1. Nothing will get misclassified. And so this is the red region, and this is the blue region, and this is the boundary that forms. Okay, but I think we would say this dot should probably, this region here should probably get classified as blue, and this is just an unusual red point. Okay, and so we would say, like if we get a test case right here in the future, we would probably want to say that should get classified as blue. And so we are overfitting, I would say. Okay, and then dots over here should probably get classified as red. Okay, and so using a higher k is going to reduce the overfitting. Okay, but the where it draws boundaries might end up being a little bit surprising. So let's do k equal to 3, and this ends up happening. Okay, and interestingly enough, with k equal to 3, we get this we get a lake here, because right here if we ask what are the 3 nearest neighbors, the 3 nearest neighbors are these dots, this red, blue, and blue, and they end up getting so this region ends up getting classified as blue, and this red dot ends up getting incorrectly classified. And interestingly enough, these 3 red dots get misclassified in the training data. And so here it is with k equal to 3. Again, here's the boundary with k equal to 1, k equal to 3, k equal to 5, and k equal to 7. Okay, and so you can kind of see the evolution of the, I don't know, the coastline. And I don't know, it's almost like the effects of water erosion on the coastline. I don't know if that even makes sense here, but it's just kind of like smoothing out isn't quite right. The coastline still has some jagged edges, but again, it gets a little bit something, right? So the coast, as the coastline changes with climate change, something like that, right? So and then when you get to k equals to 20, this is kind of the boundary that gets formed, right? K equals to 1 looks like gerrymandering. Yeah, it does. It's kind of like these weird boundaries that get drawn. And here we have k equal to 20. Something happened here with the coloring of these dots. I'm not quite sure. I probably wrote something wrong when I did the code a little bit. Okay, but this is what we have. So here is kind of the borders here. Okay, I'm not asking you to do this. I'm just asking you to just write a simple k nearest neighbors lines of code for the, I believe, the iris data set for you to try out there. Okay. All right, I don't know. Do we have any questions on k nearest neighbors? It's a fairly simple and straightforward algorithm, but it's useful and it's popular. Kind of the limitations are, as we pointed out, your data has to be all numeric in order to calculate distances. Right now I'm using Euclidean distance, but you can use other distance metrics. So there is, you can use the Manhattan distance, which is the difference in x, absolute value for the difference in x plus the absolute value and the difference of y, or plus absolute value differences rather than square distances. And then and the other drawback is if you have a very large data set, it gets computationally expensive. The process of calculating your distance to every nearest data point gets very expensive. So, I mean, you can reduce that by just random sampling nearest data points, but then you're subject to a lot more variation, right? Bias variance trade-off. So that's what you end up getting. Okay. Let's see. Should I start support vector machines? I guess we can just take a quick break here. I don't know about quick, but let me give you your first quiz answer. First quiz answer is B as in bear. B as in bear for the first quiz answer today. And then yeah, we'll go ahead and we'll take a break. We'll say five or 6 minutes here, and then we'll start talking about support vector machines. Okay, so first quiz answer is B, and then we'll take a break here, and we'll come back and do support vector machines. Okay, so we'll continue on, and we'll talk about support vector machines here. Okay, and so regarding support vector machines, this is another classification method. Okay, and we're going to just start off by talking about the maximum margin linear support vector machine. Okay, and we start here because it's simple, it's visually easy to draw, and we will talk about a little bit of the math for the linear support vector machine. Okay, we're going to start there by talking about a little bit of the math for the linear support vector machine. And then we're going to take a bit of a jump and depart from the linear support vector machine. And we're going to start talking about these non-linear boundaries. But then if I were to, and I would say, you know, probably today when you use support vector machines, it is completely all non-linear boundaries. Generally, you don't use this linear support vector machine. But if you don't understand how the linear support vector machine works in the first place, then the non-linear support vector machine seems like total magic, okay? And even today, even though I fully understand how the linear support vector machine works, the non-linear one still feels a little bit like magic, okay? Because it ends up working in like infinite dimensions, which is weird. But anyway, we're going to start by talking about the linear support vector machine, and this is the maximum margin linear support vector machine. And these examples that it can work on have to be like very simple examples, and in that they have to be fully linear separable. Okay. And if I just show you the picture, you know, it's very easy to draw kind of a boundary here. But we're going to start off with the easy case, all right? And what you do is, you know, you kind of have, you know, your red points and your blue points, or your plus and your minus, and you're going to find kind of these two parallel, what we call hyperplanes. These lines. If we're dealing in 2 dimensions, the hyperplane is just a line, okay? And it's that. The lines will separate the 2 classes from each other, right? And what we want to do is we want to select 2 lines or 2 hyperplanes that are parallel, that are as far apart as possible, okay? So I'm going to just show a bunch of examples of parallel hyperplanes that are linearly separable, but depending on how you draw these, you can end up getting wider margins or whatnot, okay? And so so what we want to do, so when we do the maximum margin linear SVM, we're going to pick the hyperplanes where the boundary is as wide as possible. Okay. All right. So here is just some sample training data. I've got blue plus marks. Okay. So these dots are in blue, and they are indicated with plus signs. And then I got some dots that are in red, and that they are in they're minus signs. And we're going to just draw kind of a pair of linear hyperplanes, right? So this, if I draw a line like this, okay, from kind of a line that's almost vertical, this counts as having 100% correct classification. Okay, I've got these dotted lines, okay, count as lines or hyperplanes that separate the blue from the red. But the margin between them, which is the distance from one dotted line to the other dotted line, that margin is fairly narrow, okay? And we can say, well, what if I take a slightly different angle or different angle, okay? And we can see if I choose an angle like this, okay, these dotted lines are still hyperplanes that correctly separate the blue from the red, okay? But in this case, the margin between them, the distance between the two hyperplanes is much wider, okay? And so we would say this one is more preferable to this one, okay? And so as we go, this is going to be the widest margin that works, okay? And there's still more hyperplanes that can be done, okay? And so this is also a hyperplane. These pair of parallel hyperplanes also do the job of separating all the blue from all the red, okay? But what the maximum margin linear support vector machine, okay, what it's going to say, pick the one with the widest margin, and it's going to say this is the boundary that we use, okay? Because the boundary between the hyperplanes here is the widest, okay? Oh, why do I sometimes have 3 points circled versus other times 2 points circled, okay? Well, here, technically there's infinitely many hyperplanes that I could use, and I just, most of them, when you find the margin, okay, as far as the distance between them, most of them will only have 2, okay? But the maximum one usually often has like 3 being selected because these two end up on this hyperplane. So this is kind of the distance that gets separated. These 2 points end up being also on the hyperplane. But you know, there's technically a whole bunch of these dots that are hyperplanes that exist in between, but they all have slightly smaller here. Okay. Do the margins have to be equally thick, the 2 sides of the black line? So so technically, this black line is one that I've drawn, which is the midpoint of the dotted lines, and I put that there to kind of help us judge the width of the margin. The margin is technically the distance from one dotted line to the other. And the black line is kind of the midpoint, okay? Which is like, if you had to draw kind of a line to split them, you'd probably draw it right at that solid black line, okay? All right, so what the maximum margin would do is it would say, this is the hyperplane that we would select, okay? So we've got these 2 parallel ones, and then this solid line down the middle would be kind of our decision boundary here, okay? And so we want to pick the ones that maximize that distance there. All right, is that okay? Just as far as visually what's happening? Okay, and clearly this would only work in your data if you have data that are linearly separable, right? Like if the original data set had a red negative dot line right here and a point that's red, there's no linear boundary that exists, and we would not be able to achieve this. Okay, if I put a red dot right here, there's no linear boundary that could separate it. Okay, so anyway, this would be the one that we pick. We're trying to pick the boundary that maximizes that margin. Okay, and so the margin is defined as kind of the perpendicular distance. Here, I have a picture right here, okay? The perpendicular distance from the decision boundary to the closest points on either side, okay? And the closest points to the decision boundary depend on the boundary that's chosen, and the ones that are the closest points, they are called the support vectors, and they lie on the margin's edges, okay? And they're called support vectors because technically you can change the location of the other data points, and the location of the boundary will be unaffected as long as those support vectors remain the closest points to the boundary. So here, let me just kind of talk about this. So this is the margin that we end up selecting, okay? This line in purple is I'm sorry, the purple is the margin, the distance from one hyperplane to the other. And these 3 points are known as the support vectors, okay? Because technically I can keep adding a whole bunch of blue points over here. Like I could add a blue point here and a blue point here and a blue point here. And the margin, the location of this margin is unaffected, okay? I could add a whole bunch of red points over here and the margin remains unaffected, okay? As long as the 3 closest points to the line is this red point, this blue point, and this blue point, the boundary, the decision boundary that we've created will be unaffected. And so this is known as, they are known as the support vectors, okay? Because if you think of the point, so you can think of points as also vectors from the origin, right? So basically these 3 points or these 3 vectors are what determine this, the boundary. Visually, is that also okay? The idea of just adding a whole bunch of points and how the location of this boundary remains unchanged. Okay. This would be a non-optimal boundary because the margin here, which is kind of the perpendicular distance from one hyperplane to the other, that's much smaller. The margin here is much smaller. Okay, so what we want to do is we want to pick the hyperplane, okay, that will maximize the margin, okay? And so I'm taking this from Wikipedia and also our textbook. And the idea is we're given n data points in the form of x comma t, all right? So x sub 1 or x sub n, this is a point that exists in d dimensions, in our case 2 dimensions. We've got a 2-dimensional point. So the xn represents our coordinate in 2 dimensions, and t represents the class, okay? Either a plus or a minus, okay? And so if it's blue, t is +1, and if it's red, t is -1, okay? And each xi is kind of in our case, the two-dimensional vector that illustrates the location of each dot, okay? And so we need to find the linear boundary so that everything with a positive class and everything with a negative class are properly separated, and that the nearest point from either group is maximized, okay? So any kind of hyperplane that we write can be set as, is the set of points x that satisfy some w, okay? W is a vector that's normal to the hyperplane, right? So if we do w transpose x minus some constant is equal to 0, this is just the equation of a line, okay? This is just the equation of a line that runs through, or equation of a hyperplane if we're in higher than 2 dimensions, okay? It's just the equation of a line or a hyperplane that exists in our d-dimensional space, okay? It's kind of like, all we're doing is we're just doing w times x, plus or minus some constant here, okay? Here we're choosing a negative constant, but that's unimportant here, okay? And when you draw this, okay, then the parallel hyperplanes that separate the positive points from the negative points can just be written as kind of parallel hyperplanes, in that if we just say, all right, the set of x that satisfies this equation, where w transpose x minus b is equal to 1, the set of x will define a hyperplane that is just, parallel on one side, and w transpose x minus b equal to -1, the set of x that defines this hyperplane will be parallel to this one, just kind of shifted over on the other side, okay? So just keep in mind what we're doing is we're defining the line, okay? In our case, the line exists on the plane x1, x2, okay? So it's basically the set of all points that satisfy this equation, right? So this is, you know, in the x1 direction, and this is the x2 direction. The set of all x points that satisfy this, the W transpose X equal to B equal to 0, plus B equal to 0, or minus B equal to 0, just plus some constant, will be this line right here, okay? And then if you say, well, this is W transpose X plus B equal to -1, it's just you're gonna get a parallel hyperplane, and over here you're gonna get a parallel hyperplane, or a parallel line in our case, because it exists in just 2 dimensions, x1 and x2. It's the set of all coordinates of x1 and x2 that satisfy this equation plus 1, and this is the set of all x coordinates x1 and x2 that satisfy this equation. Okay, I know it feels a little bit strange because we're accustomed to seeing x, this mean x and this is y, but keep in mind that this picture is the this is the x1 and this is the x2 direction. Okay. All right, and so if so, you know, if x nu is on this boundary, okay, the set of x points, then this will equal 0, and it's not going to be classified as either plus or minus. But then over on either side it's either going to end up being a positive or a negative value here. All right. Is that okay? Can we, does that make sense? So it's, so maybe I should just, this is not the hyperplane, but I just kind of want to illustrate. Yeah, I'll draw a picture here. So you can kind of think of, so, you know, you can define a, all right, so if this is x1 and this is x2, right, you can just say, what I want is, we'll just say W is equal, the vector W is equal to 1, 1, okay, and then, you know, and the vector X is equal to basically x1, x2. And we can just say, all right, W transpose X, and I'll just say plus 0 equals 0, all right? And so this will be basically all, if I multiply W times X, this is going to basically turn into the equation x1 plus x2 is equal to 0, okay? And so basically, the points that satisfy this will be if x, I'll say kind of the points that satisfy are, you know, 0, 0, 1, minus 1, minus 1, 1, 2, minus 2, so on and so forth, okay? So I'm going to just start off with, we'll say this is 0, 0, 0, and I can go to 1, minus 1, and I can do minus 1, 1, okay? And 2, minus 2, and so on and so forth. And what's going to happen is you're going to end up getting a line. It should be, it should connect all of these things in a perfectly straight line. This represents the hyperplane of x values, right? So this is, it's just a line, but it's the hyperplane of all x that satisfy, of all x vectors that satisfy W transpose X plus 0 equals 0, okay? Now, and that just generalizes to, you know, you can pick different values of W. This can be positive or negative or, you know, different things, but basically in 2 dimensions, it's going to be a line, and it's going to be the set of all points that just satisfy some kind of equation here, okay? And so I know it's a little bit strange thinking, you know, we're accustomed to just seeing lines as like y equals mx plus b, but you can also define lines as kind of just the set of all x that satisfy this thing. W transpose x plus b is equal to some constant, okay? And if I change this to, here, let me just further illustrate this, right? So if I say, well, let's have another line that's W transpose x plus 0 is equal to 1, then the points that satisfy will be 0, comma 1, 1, comma 0, 2, comma minus 1, and so on and so forth. And you're just going to get a line that's parallel. You're going to get a line that's parallel like this, okay? You can define another line just by kind of changing whatever constant this is equal to, and you're going to get basically a line or a hyperplane that is parallel to it. And that's all we're doing, okay? We're just saying W transpose X is equal plus B equal to 0. That's going to be this line in the middle. And then I define my parallel hyperplanes by saying W transpose X plus B is equal to plus 1, or W transpose X, I think on the other side I wrote minus B is equal to negative 1 and stuff like that, right? So we're just adding some constant or adding a negative constant, whatever it is, and we're defining our hyperplanes as such. Okay, and so the what we have is the margin. The margin is the vector, okay? The vector x1 minus x2. So if we have these 2 points, x1 and x2, the vector that connects them, the vector that connects x1 and x2, we can just find by taking x1 minus x2, right? So if you do x1 minus x2, that's going to be the vector that connects 2 points, right? So we think back to our linear algebra. The vector that connects 2 points or 2 vectors is just the difference vector, right? And then if you dot that vector onto another vector, you're going to get basically a vector of the same magnitude in a different direction, okay? And so we're going to dot that vector, this distance vector, onto the vector that represents the a vector that is perpendicular to the boundary, okay? So the vector that's perpendicular to the boundary is in this direction, and if we dot this distance vector, x1, x2, onto that direction, we're going to get the margin. Is that okay? Do we, are we still following here? Or no? Kind of, if we remember our linear algebra stuff. What are the dimensions of y on the previous? So y is just a constant here, okay? Y is just a constant. There's no, x exists in d dimensions, and w is a d-dimensional vector of weights. And so when you dot those two together, you're going to get a constant, and a constant plus a constant is equal to 0 or negative 1 or whatever. Okay, so y is just a constant. You don't even need the y in here. Okay. So yeah, technically we don't even need the y. Okay, we could just define the vector as this. Okay. It's not even a, yeah, not, I guess you can think of it as a z, but yeah. So normally we are solving for the W weight matrix. In this case, we're still solving for the W vector 2, correct? Yes, we are still solving for the W vector, yeah. Okay. All right, so x1, we're going to just let x1 and x2 be the closest points from the two classes, okay? And so the vector x1 minus x2 joins the points x1 and x2, right? And with the way the boundary is defined, okay? So when you define a boundary as w transpose x plus b equal to 0, okay? Then a vector that's perpendicular to the boundary is just w. W itself is just perpendicular to the boundary. So here, like if I say w is 1, 1, then the line that's defined by w transpose x is this, and 1, 1 is actually going to be the direction that is perpendicular to it. So the vector 1, 1 goes like this, and that's actually going to be perpendicular. So this is the vector w here, right? And that will hold for any kind of coordinates of w. So that's save this. I'm not sure. Okay. So like if we define like another, so whatever, however you define your w, okay. So if you define w as 2, 1, okay, and so 1, 2, 1, okay. So w is now this is the vector w. Okay, and you ask, okay, well, let's find all the x that satisfy w transpose x, you know, plus some constant equal to 0 or whatever it is. It's going to be perpendicular to it. Okay, you know, all the x's that satisfy this will be perpendicular to that line or to that vector. Okay, so the direction that is perpendicular to the boundary can just be the vector w, okay? And we can norm it so it becomes a unit vector, right? So you do w divided by the norm of w, you get the unit vector. And so if we dot that direction, that unit vector w over the norm of w, okay, if I take the dot, which is just really multiplying the transpose of that, by that distance vector, x1 minus x2, then we will get the length of the margin, okay? And just for simplicity, we're going to make the choice, we're going to call the length of the margin equal to 2 gamma, okay? It's just equal to some constant, but just for the sake of the math, we're going to just say the length of that margin is 2 gamma, all right? Is this okay so far? So we're going to say the length of this margin is 2 gamma, and that can be found by taking that difference vector, x1 minus x2, and dotting it to the direction that's perpendicular to the hyperplane. And the direction that's perpendicular to the hyperplane is w over the norm w. Okay, this is the that direction there. Okay, and so we're going to let 1 point to be on the positive boundary and x2 to be on the negative boundary. All right, so I'm going to just plug in. We're going to take these things. All right, and so I'm going to distribute the w transpose x1 and the w transpose to the x2. We're going to get this, and here I can just subtract off b and add b back on, right? So if I just add this, then this value becomes 1, right? So to go from here, I'm just adding a negative b to this value, and then I'm adding that b back on here because of the minus, and this becomes 1, and this becomes plus 1, right? So we're adding a negative, and so this cancels out the gamma, the 2, and we're gonna just say that margin, okay, the margin, or 2 times the margin, whatever that distance, what we want to do is we want to maximize basically this value, 1 over norm W. Okay. Is this all right? Okay, so what we want to do, because, because the norm of W is in the denominator, maximizing that distance, the margin, becomes equivalent to minimizing the norm of W, right? So we want to find the W that will maximize the margin, and with a little bit of math, the one that's going to maximize this margin is going to be the vector W that minimizes the norm of W. Okay. Now we can't just pick norm of W equal to 0 because we have a constraint, right? We have constraints that when we plug in x times W, okay, when x is negative, or when the label is positive, that this equation will hold true, and when the label is negative, that this equation is also going to hold true, that it's going to get labeled either +1 or it's going to get labeled -1, right? And so a clever way to summarize both of these constraints into one is we just say, okay, the product of the label, which is either a +1 or a minus, a plus or minus 1, times whatever the value that gets output, that has to be greater than 1, okay? Because the negative will multiply the negative. And so we can combine both of these constraints into kind of one statement here. Okay, are we with me still? Okay, let me give you your second quiz answer. Second quiz answer is A as in apple. A as in apple is the second quiz answer for today. The T sub I is the label, whether it is a positive blue point or a negative red point. Okay, T sub I is the label of the class. Okay, and second answer is A. A as an apple. All right, so so we want to minimize that norm, okay, which will share the same solution as minimizing the squared norm, okay, norm squared, subject to the constraint this, okay, and so optimizing a function subject to a constraint can be achieved using Lagrange multipliers. All right, so if we remember all of this stuff, Lagrange multipliers, we're going to add a new term to the objective function that we're trying to minimize for each constraint, right? So that the optimum, the new objective function, corresponds to the optimum of the original constraint problem, right? So technically, if we think about this, right, how many Lagrange terms do we have? We have one for every single data point. Every single data point will have kind of its own constraint that we have to consider. We have, we need to pick a margin so that this thing gets classified correctly on the positive side. We need to pick a margin so that this point gets classified correctly on the positive side. We need to pick a margin so that this point gets correctly classified on the negative side. Every single one of these creates a constraint in our in the thing that we want to optimize. Okay, so we're going to have n of these Lagrangian terms. That is one for every observation, as because every single observation has to satisfy this constraint. We don't want to have any points that are misclassified. Okay, so all we're trying to do, okay, all we're trying to do is we're just trying to minimize the norm of W, okay? And the norm of W squared is equivalent to W transpose W, right? So W transpose W is equal to this thing, okay? And so all we're trying to do is we're trying to just minimize this, but using Lagrange terms, we're going to do W transpose W minus whatever that constraint is, okay? And I think, in Lagrange, do you normally use a lambda? But for whatever reason, we chose alpha. It's fine, okay? So we've got a whole bunch of these, Lagrange multiplier terms that we have to include, okay? And all of these things for every single data point, all n of them, we've got this thing here, okay? So subject to this, right? All right, and so you know that. So this is where we're stuck, and technically there's no closed form solution. Okay, unfortunately there's no closed form solution, but apparently we can solve it using quadratic programming. I don't know anything about quadratic programming. I never tried to learn. I tried to read a little bit of help on quadratic programming, but I still couldn't quite figure it out. It's an iterative algorithm that you can use to kind of to solve this. Okay, so why did I bother going through all of this math to bring you to a point where I can say, well, okay, now we're stuck and we can't do anything, but we use another black box here. Well, it turns out by expressing something in this term, then I can make the next jump here. Okay, so anyway, let me just say we are able to solve this. Okay, we are able to solve this using quadratic programming once we get it into this form. And also, once we get it into this form, we can take the next step to have nonlinear boundaries. Okay, so to solve this, we can do this, and this is going to be done by, we're going to kind of take the derivative of this with respect to w and with and set that equal to 0 and solve. And we're going to take this with respect to b, because that's also a thing that we got to find, and we're gonna set that to 0 and solve, right? So at the minimum, the derivatives of this function with respect to w and b will both be equal to 0. So we're gonna take the derivative of this with respect to w, and we get w minus, and this is all, these terms go away because they don't change with respect to w, and then the rest change with respect to w, and that they're just being multiplied. And so we get at times x, alpha times t times x. And so we get this, we set that equal to 0, and we solve for w. And so w is going to end up being, and this is an interesting form, it's going to end up being equal to the sum of the x values multiplied by its label times some alpha constant. So the solution w, the solution of, you know, the boundary that we choose, the w that we choose to form our boundary, is going to be the sum of the x's, okay? And then when you solve for b, you know, you get the sum of something here. This one's less important, okay? Before I go on to the next slide, which is a little bit crazy, admittedly, it turns out that with the support vectors, it's just the alpha is going to equal 0 for everything that's not a support vector, and the alpha will be equal to 1 or have some kind of weight for the support vectors. Okay, so remember back here, we said with these 3 points are the support vectors. These are the 3 points that just define this boundary. Okay, and so it turns out that the direction that that kind of ends up just being basically the sum of these 3 points, really. The sum of these 3 points ends up being the direction that defines this line here, okay? I guess those 3 vectors, okay? And so the alpha ends up having weights for those x's that are support vectors, and the alphas are 0 for the ones that don't, okay? That don't matter in terms of defining the w. Okay, let me take this. What we're going to do is I'm going to take this w, which is right here, and I'm going to plug it back into this, okay? So we're going to take w is equal to this, and we're going to plug it back into this. Now this gets totally like a crazy mess, and my goodness, was this a pain to typeset in terms of trying to keep track of all of these subscripts. And I'm sure I'm not even, like, my eyes are bleeding just trying to make sure that I got the subscripts correct. Okay, but anyway, why did I put myself through all of this pain? Okay, it's to kind of get it into this form here. Okay, so when you do when you multiply this times this, you're going to get this whole mess, and you put this into the x. I'm sorry, you put this thing into here, and you get this, and then you kind of keep expanding. And if you pay attention and you rearrange the terms, you can combine these things, okay? And so I get 1/2 minus this, and a 1/2 minus this. So I just kind of rearrange the terms. These two things can be combined. And so 1/2 of this thing minus 1/2 of these things ends up being a negative 1/2 of this, okay? And then over here, this ends up being 0 because that's what we said, okay? This thing is equal to 0. So this thing ends up being 0. And so I can cancel that out. That can drop, and we have this. Should that transpose be outside the parentheses? Oh my goodness, you're gonna call me out on this. Let's see. It can be. It can also be inside, because this is the only thing that has a vector. This is the only thing that. So I mean, like the transpose gets distributed to all the vector elements, but these are scalar elements. So I don't actually have to transpose them. Is that okay? So so yeah, I can do this. Okay. So yeah, the transpose only gets applied to vector elements, things that have dimensions. Okay, so anyway, we end up with this, and we need to find the optimum of this. Okay, and again, there's no closed form solution. Okay, but it's interesting that that the solution doesn't contain W itself. Okay, that the solution to this to the margin doesn't include W. It's just a matter of these things. Okay. And we need to find kind of the set of the alphas, right? The alphas are really the only things that we can mess around with. The set of alphas that will do this. And it turns out that the alphas that that satisfy are the ones where, and I already mentioned this, I forgot it, and this separate slide. The alphas are 0 for all the non-support vectors, and the alpha, the values, the x's that do count, will have an alpha that is not 0, because those influence what W ends up being, okay? And you can think of alpha as a measure of how much influence a particular value in the training data will have on defining W, okay? And so, so figuring out your margin is basically a matter of figuring out which values in the training data are the support vectors and matter. Okay, so why have I bothered belaboring all of this time on this? And I'm gonna run out of time, unfortunately. Okay, is that once we get things into the solution, into this form, we can start talking about other aspects like soft margins and nonlinear boundaries using using the kernel method. Okay, and so when we created the maximum margin classifier, we had this constraint that whatever point you have, whatever label it is, when you multiply it by that x value, it's got to be correctly, it needs to be on the correct side of the boundary. It has to either be greater than 1, or, and if it's negative, then this will be negative, and the negative times the negative, that also has to be greater than 1, okay? This is what we call a hard margin, because it forces all of the data points to have that after we multiply it, that how far it is from that boundary has to be at least 1, okay? We can quote soften the margin by saying, you know what, it does not have to have a distance of 1, but it can actually have a distance less than 1, okay? And so, what the picture looks like for this is that so if you have something like this, and let me just, I don't know if I'm able to draw dotted lines, so I'm going to just draw kind of thinner lines. All right, when you have the soft margin, what it does is it allows you to have, so most of our dots are, you know, you've got points like here and here and here. And the soft margin allows you to have points that are inside the margin, okay? This will be where when you multiply it, it actually doesn't end up outside of the margin. It ends up within the margin, okay? And in fact, you can even allow for some points to be on the wrong side of the boundary, okay? You can even allow for this, okay? Now, obviously, when you do that, it's gonna that doesn't feel quite good. And so what ends up happening is we, to incorporate this, we just say, you know what, we're going to set an upper bound on what alpha can be, okay? So it used to be that, let me go back a few slides, is that, oops. So right now, we said this is kind of the optimal boundary, okay? But what if I put in like a blue dot right here, okay? If I put a blue dot right here, or here, if I put a red dot right here, then this will have to be kind of the optimal optimal boundary, because over here, if I put the red dot, then this would be misclassified under the kind of the traditional answers. And so, you know, we don't want one point to have so much influence. So what we do is we put a cap on how much influence a single point can have. Okay, and that's going to be kind of a constraint, and it puts an upper bound on how much influence a single point can have on defining the boundary. And so that allows for soft margins. Okay, and then and also getting data into that form allows us to use something called a kernel function. Okay, so right now what we have is we're defining our linear boundary by trying to maximize this. Okay, and we can find nonlinear boundaries by trying to maximize what we call a kernel function. So this inner product, x transpose x, can be turned into a kernel product, okay? Or a kernel function, right? So this inner product of xm and xn, okay, can be turned into a kernel function. So what's a kernel function? A kernel function is just the inner product of vectors after we apply some kind of transformation function. All right, so we'll see how far I get, and I might have to continue this on Monday, but we're just applying a transformation function to xm and xn before we take the kind of the dot product of this, or the inner product of it, okay? So you have some kind of transformation function. Sorry, this is a different looking phi here. To the vector xm and xn, okay? So, for example, we can take a vector, a point in 2 dimensions, and apply a function that transforms it into 3 dimensions, okay? So I could define some function phi and say when you apply phi to the vector x1, x2, the transformation function returns a 3-dimensional vector, x1, x2, and x1 squared and x2 squared. Okay, so all we're doing is we're taking our point that exists in 2D and we're adding a 3rd dimension, or we're applying a function that transforms it into a higher dimensional space. Okay, this is an arbitrary function. I've chosen this because it follows. There's a visual example that I can present here, but this function phi can be whatever you want it to be. Okay, now there's certain functions that do well, and we'll see this, okay? And so if this is the function phi, then there's a corresponding kernel function that that we can use, okay? But let me just show you what happens when I apply the function transformation function onto this coordinate 1, 1 and another point 5, 1. Okay, so if I apply this transformation function, which returns x1, x2, and the sum of x1 squared and x2 squared, then this point 1, 1 gets transformed and it becomes this three-dimensional point 1, 1, 2. Okay, because it returns x1, x2, x1 squared plus x2 squared. So 1, 1, and 2. Okay, and then when I apply it to this coordinate 5, 1, or this vector 5, 1, it's going to return x1, 5, x2, which is 1, and then x1 squared, 5 squared, plus x2 squared, 1 squared. 5, 1, and 26. Okay, and therefore the kernel function will return the value 58 because it's the inner product of these vectors, right? So I take 1, 1 and 5, 1. When I apply the transformation function, I get the vectors 1, 1, 2 and the vector 5, 1, 26. And when I take the inner product of those, or the dot product of those, I get 1 times 5 plus 1 times 1 plus 2 times 26. And this adds up to 58. All right. So this is just kind of an arbitrary thing, okay? And the thing is you don't actually have to transform it into 3 dimensions and take the inner product. You can, that's a completely valid way of doing this, but you can also just kind of, in this case, if this is the transformation function, the corresponding kernel function is going to be xm times xn plus the norm of xm squared times the norm of xn squared, okay? So without even bothering transforming it into 3 dimensions, I can get the same result, right? So if I have the points 1, 1 and 5, 1, I could transform it into 3 dimensions, take the inner product, and I get 58. Or I can apply the kernel function, the corresponding kernel function, which is this, directly to my 2-dimensional function, okay? And if I take the inner product of 1, 1 and 5, 1, I can get 1, 1, 1 times 5 plus 1 times 1 plus 1, which is 6. And then, and I take this part, which is 1 squared plus 1 squared, multiplied by 5 squared plus 1 squared. Okay, so I get 2 times 26. Okay, and this this ends up being 52. 6 plus 52 ends up being 58. Okay, so I can apply the kernel function directly to my 2-dimensional vectors. I don't even have to worry about what these values, what these vectors look like in 3 dimensions. Okay, I don't actually need to know what phi looks like. When I transform phi into this, I'm going to get this and this. I don't even need to know what this looks like. I can just apply the kernel function and get this number 58 directly. All right, but I do this to kind of show you that this is the idea behind a kernel function. That a kernel function has a corresponding phi transformation function, and you're applying the phi transformation function to the 2-dimensional vector, and you're then multiplying you're taking the dot product of those resulting transformed vectors. And when you take the dot product of those transformed vectors, you get this scalar output, okay? And that's our answer. Or you can just apply the kernel function. In this case, it's this, which is going to also produce the same scalar value. And you don't actually have to do the transformations, okay? And it's not the idea, and you might have a kernel function and you might wonder like, oh, I wonder what the corresponding transformation function is, okay? That's not the point of the kernel function. You don't have to actually figure out what the transformation function is. You can just use the kernel function directly, okay? And so here's a visualization of using the kernel function and how we can do it for support vector machines here, okay? And so we're going to start off. Okay, so it's a little bit hard to see, but we've got dots that are blue right here inside the circle, and dots that are red outside the circle. Okay, and the data exists in 2D, and in 2D, there's no linear boundary. There's no way to separate the blue points inside the circle from the red points that are outside of the circle. The blue and red dots are not linearly separable. okay? And so what we're going to do is we're going to use the polynomial kernel to transform our 2D into 3D data, okay? So this is what the picture looks like. So we're basically taking our two-dimensional coordinates and we're applying a phi function to transform it into 3D, okay? Okay, so this is what's happening. We're applying the function so that it goes from 2D into 3D, okay? And so, so the data now exists in 3D, and once the data exists in 3D, you can then find a linear hyperplane, okay? A linear hyperplane that separates the blue from the red, okay? So once you've transformed the data in 3D, a linear hyperplane does exist that separates the blue from the red, and that can be used to define the boundary that separates the blue from the red points. Okay. So again, our data exists in 2D. There's no way to separate them with a linear plane or a linear hyperplane in 2D. But then if you apply a three-dimensional transformation function, then you can find a linear hyperplane that separates the blue from the red, all right? And that's going to form our boundary here, okay? So that's what's known as the quote kernel trick for support vector machines, okay? And we have a whole bunch of different kernels that can be applied. You can look at this Wikipedia article on positive definite kernels, and they have a whole bunch of these things that that can be used. But basically, it's just you've got some kind of kernel function k that that gets applied, right? And so the linear kernel is just x times y, or you know, x1, x2. And with the polynomial kernel, you know, you're doing all sorts of stuff. Okay. Are there, question says, are there situations or aren't there situations where data is even more randomly distributed than that? Yes, and you'll need like 40 different peaks in the 3D function to make it so that you can, yes, absolutely, yeah. So these are, we're just starting off with toy examples, okay? We're just starting off with toy examples because we can illustrate the toy examples. So one of the most popular kernels is known as the Gaussian kernel, or the it's also called the radial basis function, okay? So if you look up the radial basis function kernel, or also known as the Gaussian kernel, this is a transformation that actually exists in infinite dimensions. It's based on the, so if you think of the exponential function, there is a Taylor series that can be used for there's a Taylor expansion of the exponential function, right? And that's an infinitely long expansion. And the Gaussian kernel, what it actually does is there's a corresponding phi function, okay? A corresponding phi function that will expand this, take this function and take the Taylor expansion and expand it into infinitely a product of that's infinitely long, okay? And of course, we don't actually want to do this phi transformation, which is going to transform it into infinite dimensional space. And we don't even have to worry about what that phi transformation function is because the result is you're going to get back a scalar value, right? So we could technically, theoretically, we could take the function, take the coordinate, transform it into infinite dimensional space here, and then take the inner product and get back a scalar. Or we can apply the kernel function directly, don't even worry about the infinite expansion, and get back the same scalar value. And that's what we're going to do, okay? And that's what we do when you use the Gaussian or radial basis function kernel, is that there's a corresponding function that transforms it into infinite dimensional space, and it will create a projection in infinite dimensional space where a linear boundary does exist, okay? We are not able to picture this, and you don't actually need to know what this transformed space is. Okay, I know I'm going a little bit over time, but let me just kind of show you. So here's an example where it's totally, you can't separate this, okay? And you've got basically, this is your homework exercise. And it looks like I've got like 30 slides left. These are all just a whole bunch of pictures here, okay? Basically, if I try to do a linear thing, it totally fails, right? But I can take, let me just kind of jump ahead, and I can apply the radial basis function kernel along with a soft margin, and it creates these interesting shapes that separate, that kind of create a boundary between the red and the black points, okay? And there's a few different things that you can mess around with. There's two parameters when you use the radial basis function. There's a gamma and a cost parameter, a gamma and cost parameter, and this allows for different shapes, okay? And so this is the result of projecting our data into infinitely high dimensions, finding some linear hyperplane that exists in infinite dimensions. Again, it's a linear hyperplane, which our brains cannot picture in infinite dimensions. And then we're projecting it back down into 2D, okay? So it's basically that video that we saw, but this one projected into 3D and then back down to 2D, okay? We're projecting it from 2D into infinite D, finding a linear boundary, and then projecting it back to 2D. And this is the boundary that gets drawn. And so you can get these very complicated boundaries that get drawn from just using the radial basis function kernel, because it's using the Taylor expansion, which is an infinitely long expansion of the exponential function. And so depending on your choice of gamma and the cost, you can get these shapes that, you know, maybe this is overfitting at this point, okay? Maybe it's not, okay? And there's a few different things. And for your homework, I just want you to mess around with picking different gamma values and different cost values and seeing if you can understand what these parameters, what effect these parameters have on kind of the boundaries that it will form, okay? All right, so let me see. The question says, wait, in the 3D function, to make a plane separate red from blue. So every contour line we see is where that hyperplane cut up our infinite dimensional graph. Yeah, so all of these lines, so these are parallel, quote, boundaries in the infinite dimensional space. So this is the boundary, the heavy black line is kind of the boundary that gets formed. And then I also have kind of parallel hyperplanes that exist. And the thinner black line and the thinner red line are kind of the shadows, quote, shadows of those parallel hyperplanes, if that makes sense, okay? So like, it's a lot easier to see here, right? So here I've got the one linear hyperplane, and these are the parallel hyperplanes that exist, the black and the red lines. And this is kind of the same thing, but projected in higher dimensions. The black line is the hyperplane that separates them in the middle, and then the lighter black and the lighter red lines are parallel hyperplanes that exist in higher dimensions that get projected down. It's a weird thing to think about, all right? Our brains, at least my brain, can only picture things in 3D. That's the highest dimension that I'm able to think and visualize in, okay? I'm not like, whatever, Mrs. Who's It from Wrinkle in Time that can exist in high dimensions. And I can't picture this, but it's the idea that we're going from 2D or whatever dimension that we're existing in into a higher dimensional space, finding some hyperplane there, and then projecting it back down there. So the best visualization I have is this thing that goes from 2D to 3D back down to 2D. And we're doing something similar, except we're not projecting it to 3D, but infinite dimensional D, okay? And so these slides, I would say, you know, scroll through these slides. These are just meant so where you can kind of just flip through them and see the different effects of picking different gamma and cost values. And you can see how the edges get really wiggly or you know, different things happen as we mess around with this. And basically in the homework, I just ask you to figure out what effect does altering the gamma and the cost do, because probably if you ever use support vector machines, you're probably going to use the radial basis function. This is it's one of the most popular choices for a kernel for a support vector machine. And it's important to understand the effect of these parameters. Okay, sorry for going a little bit over time today, but that's all I got for you guys. And so have a good weekend. Did I give you the last quiz answer? I didn't, probably, right? Okay, last quiz answer, third quiz answer is E as in elephant. E as in elephant. That is the third quiz answer for today. And that's it. Have a good weekend, you guys, and we'll see you on Monday.